I am Rabia Bilgücü, an assistant student at the Smart Cities and Digital Ecosystems Lab. This is the first of the seminar series organized by TOBB to the Smart Cities and Digital Ecosystems Lab. The talk will take around 45 minutes. Approximately in every 2 weeks, we will have distinguished speakers all around the world. To introduce our invited speaker today, I first give the word to Professor Dr. Mehmet Akşit, who is the head of our lab. Thank you.
Thank you very much, Rabia. I'm very pleased to and honored, of course, to give the word to Professor Tekinerdoğan. We know each other for a very long time. He is the head of the Information Systems Group at the Wageningen University in the Netherlands. Wageningen is one of the top universities in the world, especially specialized in life sciences. Professor Tekinerdoğan has got his BSc and MSc from University of Twente, and PhD also from University of Twente in 2000. He has worked at Twente for some time and then went to Bilkent University in Ankara, came back and went to Bilkent again. And finally, since several years, he has been a professor and chair of the department at the Wageningen University. He has many specializations and he could set up a large group, one of the leading groups in software technology and life sciences, I mean. What I could say, of course, we will hear more from him. What I could say is that he is very talented or specialized in setting up large systems and what I would say system solutions to large problems. So was able to actually, especially in the recent years in the life sciences, and was able to set up, as I said, a large group. Now, I please welcome Professor Tekinerdoğan for his talk. Thank you.
Thank you, Professor Mehmet Akşit. Thank you, Hocam. I was actually raised by Professor Mehmet Akşit, I should say. I had the pleasure and the chance to grow in his group, Software Engineering Group. So many ideas I also got from him. I would like to thank him also in this today. Today I will talk about, so it's my pleasure that you have invited me, and I will talk about system of systems, but I've chosen a particular perspective, a critical system of systems, and in particular, how to architect or design this system. It's a life science university, Times Higher Education 52, or so it's the number 1 in the Netherlands. And I'm in the social sciences group, the information technology group. I'm the chair of that. Recently also the chair of the business science cluster, which actually covers 5 chair groups within the social sciences. Our focus as a group is actually, it's an information technology group, right? Sorry. I don't need to get rid of this. The information technology group. So when I started 2015, so we had to provide a vision. So then we said, like, everything will become smart, everything will become connected. And so our vision and mission is still the same, I should say. So we are focusing on smart systems and in particular system of systems that appear to be the right track. And not only for life science, but also for all domains. When I started as a group, actually, we had like the half of the staff members, and we didn't have PhD, just 2 PhDs and no postdocs. The group has grown dramatically. all consist of all very smart people doing very nice stuff, and we are creating actually or working at different domains. You can reach me at through LinkedIn. I will be happy to connect with you. On ResearchGate, you can find or papers about 80% you can download there. If you can't download these, I will be happy to share it with you. And now and then I post something on Twitter. What I will talk about today is like architecting critical system of systems. So I will start first with what is a system, actually, then move on to system of systems, and what does it mean to have a critical system of systems, and related to this also the critical infrastructures, and finally the challenges for architecting critical system of systems. I will not propose today any solution regarding the design evaluation, but I will identify some of the challenges and provide the overall context and vision about this important topic. So this is the parable of the elephant. This is used a lot in systems engineering domain. It is used in different traditions, among which also from Rumi, right? For those of you who know him, right? So it is like a parable like this elephant, and there are here like several people who have never seen the elephant, and they are blind or blindfolded, right? So they cannot see it, and they have to touch and then say make sense out of this system, right? And one says like, oh, it is a spear, right? They each feel a part of the elephant, and the other says it's a snake, the other says it's a tree, it's a wall, it's a rope. So each of them have a partial perspective. That's a quite interesting story, because this happens to us all, right? So we don't have the absolute truth of anything, right? Always our knowledge is limited, right? And the essence here is like you should look at the broader picture. You should look from the holistic perspective to make sense of the complex world of the systems, and don't apply reductionistic reasoning. Systems thinking by itself is really interesting, and many problems need to be solved from that kind of thinking level, right? So the essential lessons that we can learn from that is like that a system cannot be known or cannot be built, I would also say, like by just considering the atomic elements of which it's made, right? We need more than that. If you do this, then it's like more a reductionistic view, right? In contrast to a holistic view, systemic view. Now, if you look at this, so what is actually a system? Right? You say we use this all in engineering disciplines, science disciplines. What if you ask, for example, students, what is this? How do you define a system? Right? Sometimes you don't get a clear answer, right? So if I would ask you, I don't know whether we will have some interaction here. Is this a system, a pile of bricks, right, or a plate of pistachios, right, or people waiting for the bus? Is that a system? And if so, or if not, why? Anyone? Yeah, you can maybe just speak up if you like, otherwise, yeah, not sure. Or let me say like this, why is each of this not a system? What is missing? It consists of elements, right? It has elements that is essential for a system, but it's not sufficient, right? It's not sufficient because it's actually like what we say, it's a group, a set of things, but each of it does not have a purpose, right? It does not have any relations, right? And that's actually what brings us to the definition of system. Oh, I see, there are chess. I can see too, okay? Relations are missing, indeed. Very good, Sina. A system, by definition, consists of elements, but it should also interact. It has interactions among these systems. And above all, it has also a purpose, right? If one of these issues are missing, right, if you don't have a purpose, or if you said don't have interaction, it's not a system by definition. So for a system, or if you talk about system, you say like consists of elements, interactions among these elements, and it has some purpose. As you can imagine, so developing a system is thus not that easy, right? It's not just a bunch of people or a bunch of things together, right? But these systems, these elements should work in a coherent manner and have a common purpose, right? Well, if we move on, that's actually the three elements, and then this is discussed a lot in the systems thinking or systems engineering literature domain. For example, in Peter Senge, right, the fifth discipline. This was published. I read this book 20 years ago, but then from a different interest, right? So, but this is like here he talks also about the what does it mean to think at the systems level, right? And there are three essential levels which actually recur and which is repeated all the time: purpose, elements, and interconnections, right? So, and that's the systems thinking discipline. Many problems are not solved because we lack the systems thinking approach. Beyond that, so where is it like? So that's the system definition. Now, what about system of systems? That's the from the it's more recent than the notion of system. This actually broadens the scale of the system element. So the systems thinking approach says like you should look beyond the element level, don't be reductionistic, right? Look at the purpose, look at the elements, and check how they actually relate, interconnect. And the system of systems goes a bit further. It says like, well, you could also integrate these independent systems, right? And this integration is called the system of systems. Right? That's a broader level, right? So, and in essence, why is that necessary? Well, we already said like each system has a purpose. It consists of some sub-elements. It's interacting sub-elements, and it has some purpose. It has some capability. But a system of systems integrates further these independent systems to create additional capability, which cannot be created by each of these substituent elements or systems, right? We say like the system of systems actually reflects the idea of that it's more than the sum of its parts, right? So you have like S1 to Sn, each create, for example, capability 1 to n. But if you have system of systems, you create another capability which could not be created by each of these systems. If that's the case, we talk about thus a system of systems. So system of systems as thus consists of several systems, and it actually adds also additional properties. Right? It says like, well, you talk about system of systems. Again, if you have like independent systems, right? So you have like systems, and these should be like each system should be operational interdependent, independent. Each of them should be managerial independent, right? And so they consist by themselves, they have value by themselves. And when you put them together, they create kind of emergent behavior, right? Because I said like, you create some value which was not there in each of these systems. It has evolutionary development. So it is developing system of systems is not easy. Usually it evolves, right? It's a decentralized development, and very often it's like geographical distributed. It's not at the same location. If you have these properties, and in particular the first three properties, we talk about a system of systems. Here it's interesting to know that if you put several systems together, they can actually show different kinds of behavior. So when we say like you have to create additional value, which means like synergy, right? It is not just putting a number of systems together, but that if you don't do it well properly, they can also interfere, right? Which is shown on like in this cartoon, right? So you really say like creating additional value. So you put systems together, but if it's not done, you can actually impede the value and then decrease the performance, decrease the effectiveness, decrease the efficiency. So now we have this situation. We started with a system, and we say like we have a system of systems. System, by definition, is called has its elements. They interconnect. They are interconnected. They have a purpose. A system of systems is a system, by definition, system of systems, right? But it has also additional constraints on this system. They should be operational independent, managerial independent. You have like emergent behavior, and there are aspects of evolutionary development and geographical distribution. If you look at the configuration, right? So each system element has a capability. System element can be at the lowest level, or a component or element, can be subsystem, system of systems. And you see, you can develop different kind of system of systems. Examples of system of systems. If you look outside the whole universe, our planetary system or universe is actually a system of systems, right? And each, for example, the planets, each of them by themselves is a system by itself. They actually are related to each other. You get one of them out, and the whole thing will show a different behavior. You could say, what's the purpose, right? That's the telos. That's a more philosophical discussion. And so, ecological system, ecosystem, right? It's a system of system. You could say, like, even the social system. You see, like, you have like a person. It's a system, has a goal. A person lives in some family or some, right, or neighborhood or city, right? And social system, right? You could say, well, that's a system of systems, right? Interconnecting, they can they create additional behavior, right? So you create additional behavior if you are in a family, for example, or if you are among friends, or if you are in a nation, right? Then social system is a system of system. Farming system of systems at your university, right? So recently with the precision farming, we said like you have a farm management system, but if you integrate this weather data system, seed optimization, farm equipment system, irrigation system, you can create additional value, which you cannot create from each of these separate systems. Health information system of systems. I had 2-3 weeks ago also talk for the USEP, right? So in Turkey, yes, I try to also integrate all these information systems together to create additional value. And we try to do it here also at the Netherlands, right? So we are also working several projects. It's a system of systems, right? So we have like patient information system, nurse information, pharmacy, radiology, etc., hospital information, and each of them is operational independent, managerial independent. They are located at different cities, but if you integrate these together, you can create additional value for the patient, for the doctors, for the government. You can lower the cost. You can provide better service. That's the whole idea. Logistics management, supply chain, also from our university. You have suppliers, manufacturers, warehouses, customers, and each of them actually are integrated, and so you can create additional value from this system of systems perspective. What happened next? So we have said like these systems are, so we have this element level, system level, system of systems level. So systems become connected. And we have seen also an additional, a separate development, that is like the digitalization. First start with the computer, the digitization of the physical elements to digital format, which is called the digitization. Now we had like different digital solutions, like big data, machine learning, AI, etc. The use of these digital technologies is called digitalization, and now if it leads to a disruptive change, we call this the digital transformation. So this has led to what we say like the pervasive computing. So there's like computing everywhere, right? So, or we have changed the world, right, with all these digital aspects, for the good or the worse, so or the bad. But that's the situation, and this has also an impact on the systems. But we say like the systems, and the conclusion here, very important and short conclusion so far. These systems get smarter and connected, right? So, and we see this happening in different domains. The banking, finance, defense, and even the life science, right? So even our university, like maybe 20 years ago, had less to do with digitalization. Now it's like we are talking about connected life sciences, farm equipment, farming systems, which become smarter, where we use lots of AI and software. That's happening. So we can say like we are now talking about cyber physical systems as well, right? So on the one hand, we have the sea, air, land, space, right? That was there already, and we saw already some systems connecting to each other. And now we put also the cyber world, and which is also growing. And we talk about this, that the notion there is like the cyber physical systems. And the interesting thing there is like the cyber part. It's a separate world, but it's also starting to actually control the physical world, or the physical world becomes dependent on the cyber worlds. Quite very interesting, and all these things are happening so fast, right? And we are in the middle of it and actually also contributing to it. Cyber physical system of systems. Examples of system of systems, for short again. And technological, social, natural. Yeah, we can see them all around if you look at it. So we see elements, we see systems, we see system of systems, and then everything is so complex and so fascinating, right? I try to actually to classify the system of systems, and you can check this in this paper, multi-dimensional classification of system of systems. I think you can download this from ResearchGate. If not, please let me know. And you can, there are different kind of independence of these systems, the geographical distribution, the evolution can be different. I will not elaborate too much on this here, but emergent behavior, anticipate, non-anticipate, configuration, etc., etc. So you can find different kinds of these. And one important issue that is used to distinguish the system of systems is by looking at whether they have a common purpose and then common management. If they don't have common purpose, like you have like the internet, you have like all these different systems can collaborate with each other, but there's no common management, common purpose. We call this virtual system of systems. If they have a common management and common purpose, then we get here actually, they can be either the subsystems can retain their ownership, and it becomes acknowledged system of systems, or not, then it's a directed system of systems. For example, like in the defense industry, right? Directed system of systems, right? You design them one, right? And there's one management, one purpose. But like acknowledged SOS is like a health system of systems, and usually they are like different owners, but there's a common purpose, common management. And you have like collaborate SOS or federated, where say like it's a common purpose. There's not, but each typically have like more distributed way of systems integration. But this is one key purpose, that's what you see often in the literature. But you can also classify them based on different issues, which I not elaborate too much on. but please check that. One important issue of system of systems, please check the paper that I have referred to. One important issue that is for the system of systems is the emergent behavior. And that's actually the interesting part, maybe. We also talk about sometimes complex adaptive systems. There are many systems, and they also they come together and they create something new. And you cannot create it at the separate level, like a flock of birds or something else, right? So, and you see this also in the nature, but also now in the digital systems, right? The software systems, you put them together and then suddenly you see like something new can happen. And that can be actually, you can actually anticipate on that or not. But this is one of the challenges also of the system of how to model, identify, manage these emergent properties and how to make sense of these emergent properties. That is, what is the behavior and how to model that. That's really a fascinating research, I should say. This is a figure from this paper where they actually have provided dimensions of emergent phenomena. So the emergence you can apply to the structure of the system. It can change on the behavior. It can be predictable, unpredictable, or it could be more stochastic or deterministic. You can explain it, and there could not be explanation, or it could be in principle, or you could by rules, by simulations, or by analytics, right? Consequences could be like positive, none, or negative, right? So you see like emergence. So typically if systems are in a synergy, and you have like a positive relation, positive value creation. This is more like interference, so where we say like negative, but sometimes it's neutral. So you see like, so you can anticipate only changes. You cannot anticipate. The outcome could be positive, outcome could be negative. You can understand, you cannot understand. The behavior could be deterministic, stochastic, or chaotic, even unpredictable. And if you look into this is really so fascinating. You say, oh, what's that? Life is some parts really so intelligent. Some, and you also see like that we don't understand too much yet, I should say. And we try to make sense of it, right? So from the nature, right? And all these systems. So system of systems. So in this one, if you look at these classification, you can, from my classification, you at least 26 separate types of systems, right? So the technological, like knowledge, etc., etc. So when we talk about system of systems, it's not just one type. There are multiple types depending on the different kind of behavior. Well, we can look at the system of systems from different perspectives. You can say like, how effective is it? How scalable is it? What is the value? What is the cost? What is the reuse? And so these are all interesting aspects, but I want to actually focus more on the critical aspects. And so I said, like already, these systems are systems become smarter, systems become connected, and actually, what I also said, like we create this system of systems. Very often they are like software controlled, and they actually control the physical systems. Actually, they control our world, or which means like we are dependent on this system of systems. Dependability as such is an important issue when we talk about system of systems. What is dependability? Well, actually two perspectives. Say like it should deliver the service, and that I can trust, that we can trust, and there should not be service failures, right? And should not be. There could be maybe, but should not be frequent. That is annoying or that is observable. Very short definition, right? So it means like, so, okay, we create all these system of systems. It should create value for us, but it creates value for us, but also it creates also dependency. I'm dependent. We are dependent on the system of systems. We are dependent on the healthcare system of systems, farming system of systems, banking system of systems, defense system of systems. You see, like that's, yeah, that's a critical system of systems. Ensure that these system of systems work well. You see, I use the term now critical system of system, and later I was saying there was the term critical infrastructures. Critical infrastructure is a system of systems, critical system of systems. And this is a valued issue because, like, so imagine, like, from the security perspective, we have like one smartphone, and we say like it has an attack surface, attack space, right? From outside, it can be attacked, right? The adversarial attacks, like the microphone, camera, location, etc. And they can hack your smartphone. With the smart car, it's nice, it creates a value, but it has also some kind of attack points. So it's not easy to build such a dependable, smart, self-driving car, for example. It's not that easy, and we should take into account many of these critical aspects. Well, and this is for a single system. And what about the system of systems? Then the problems gets even bigger, right? So that is like there could be, because on the one hand, you actually integrate all these systems of systems. Each of them could be by themselves, have their own threads, and if you integrate them all, suddenly you can share the threads, right? Here's just one example of there are many different examples where it went wrong. Northeast blackout. This is used a lot. I used this in my software testing courses. And Northeast blackout of 2003. It's almost 20 years ago, but these things happen now and then. Like it was. There was at 2003 in the northeastern, midwestern United States and Canadian province of Ontario, and 508 generating units and 256 power plants were just shut down. And that was the reason for this was just a simple software error, release condition. I explained the software testing course. It's quite interesting, but it was like it had a trigger effect on all these different kind of systems which are connected. And people didn't know what happened and that in the first place, right? There's a movie here. I don't know whether it's working. What's the time? Can you see the movie? I hope. I don't know whether you can hear it. So I hope you cannot hear it, I guess. No sounds. Yeah, you cannot hear the sound, but please check this on the website. What happened here is like, okay, the power outage, but it impacts the whole society, right? So no electricity, nothing works, nothing seems to work, no lighting. So it creates a complete chaos. We say like this is a critical infrastructure, critical system of systems. Yet another one, communication system from AT&T. This one is a bit older, but these things still happen, right? And even and the chances are actually even larger, bigger for this, right? January 15, 5 million calls were blocked for 9 hours. And that was a simple program, a C program. There was a break in the whole program, but the program thought it was for the if block, but this was actually for the whole entire switch block, which actually again had a kind of trigger effect. Obviously, we are dependent on these system of systems. They create value. When we integrate all these systems, we can create value. which cannot be created by each of these separate systems. But we have to take into account that we are dependent on that. So they become like critical, right? And first, with the before the Industry 3, before the digitalization era, and now with even with the Industry 4, we had only to cope with the physical threats, and now also with cyber threats, right? So then the problem got larger and more complex. So we can do more, but we become more and more connected to these systems. We become more and more dependent. These systems become more and more critical, right? And this is an issue that we should really is a serious issue, because it can have a disruptive impact on the whole society. What can we do? We could say like, well, don't just close everything. Don't connect systems. Don't use internet, right? Then you are 100% secure, right? Isolated. Of course, we cannot do that. One, that does not seem to be a feasible solution. So these current systems are connected for some purpose, right? We try to connect these farming different systems or health information systems for some purpose, to create additional value. And so, but that brings additional risks with it. So the idea, as I said, like this critical system of systems, often called like critical infrastructure, or I can say like each critical infrastructure is a system of systems, right? And system of systems, it's not just like a technical system, it could be also a social system, and always like related to the social systems, the governance, and in technical system could be like physical part, software part, right? So mechanical part, right? So so that shows us it's not that we should think broader than our own discipline. Like it's not just like the software, or not just like electricity, not just like mechanical, not just governance, but it's actually also at the disciplinary level, right? So we should look at the, as I will show in the later slide, we need more like interdisciplinary or transdisciplinary approach. And there are a bunch of these critical systems, critical infrastructure, agriculture, commercial facilities, the dams, energy, information technology, right? The communication, transportation, government, defense, communications, chemical, right? Healthcare. You see, all of these systems, we have to deal with them, and they say like typically they are a system of systems, and if this one of these systems don't run well, they will impact our society. So dependability on system of systems. So there are three dimensions here. There are attributes, threats, and means. I will go shortly over this, so I'm be quick. Dependability and security. Dependability has been discussed a lot, and then later on security was added for criticality, right? Dependability is like, what does it mean dependability? Well, it should be available, the system. So, and if I have like, I need a healthcare service, it should be available. I need communication, it should be available. It should be reliable. It should not be, there should be continuation of the correct services. It should be safe, and it should not be life-threatening, or the, for example, integrity. It should be absence of improper system alterations, right? It should be maintainable, right? We should be able to, as I said, system of systems is evolving. We should be able to maintain it and change it and repair it. And security, especially also cyber security, lately, protection from adversarial attacks. So if you look at this, that's the attributes. The second part, the threats. There we have the notion of three issues, like a fault, error, system. A threat is that things that can affect a system and actually drop the dependability. In dependability literature, let's say like the fault, right? You could have, for example, software fault, for example, wrong initialization of a loop that could lead to some error. right? Or like in the case of the brake, that was just like, that's a mistake, so it leads to an error, and that can lead to a failure. The failure is like, for example, collapsing or power outage, or the telephone does not work, right? Or some more even critical, like in the defense or healthcare. And so that's a different kind of failures you can have. And the third one is the means. What can you do with it for it? Well, you can try to prevent it, you can tolerate it. Fault prevention, right? Prevention of fault avoidance. Fault tolerance, you could say like, well, you could say, well, every system is complex. It's not easy to eliminate all these faults, but we could actually tolerate, we could recover it. Fault removal whenever, or recovery whenever something wrong has happened, you should be able to correct it and quickly. Fault forecasting, you could already predict what can happen. And so the attributes, what we said, the threats and the means, that gives this kind of story. When we talk about critical system of systems, thus we say like, okay, it means like dependability and security is an important issue. And then we have to take into account several quality factors. Now, and we have to know what are the faults, how to deal with errors and failures. And these are our approaches. This is a nice paper from RPCN. This is still, it's almost 20 years ago, but very nicely summarized all these different concepts. Okay, that brings me to the last part of the talk. I said, like, I start with system of systems, critical system of systems. What about architecture design? Well, architecture, so this is every system has an architecture. Right, that's this story, whether it's simple or complex. In a system of systems, critical system, it's indeed a complex system. But it is good to actually model this architecture, right? Why is that? Well, if you don't model it, we cannot understand it. If you don't understand it, we cannot control it. And for a critical system of systems, it is essential that we can have some insight in it and that we can somehow control it, right? Or manage the non-desired emergent behavior, right? So we should be be able to we should, it's the rationale for software architecture, I should say here, put like system architecture or system of systems architecture for understanding, communication, coping with evolution. For a single system, it's already it evolves, but a system of systems evolves continuously, right? It is an inherent property for guiding the development process, for supporting the organization, the governance, the management of the system of systems. And for a single system, we also for providing gross level views. So we need to model the architecture. And for modeling the architecture, of course, we need to know the stakeholders, especially for a system of systems. So we had this workshop about health information systems. So one important task that we had applied was like, who are these stakeholders for this health system of systems, healthcare system of systems? See, and that is very crucial question, because you have to know these concerns of each of these stakeholders. Doctors have different concerns than, for example, lawyers, than, for example, persons who are related with ethics, right, on the patients. And to ensure that you have the right system of systems, right? So so the idea, and when so these actually form the architectural drives, and the architect should be able to design the system of systems based on all these different stakeholder concerns. For modeling, we typically use the architectural views. For a single system, it doesn't fit in one view. So we typically have like multiple views or plans. The same we will need for the system of systems or critical system of systems level. And there we use the notion of architectural viewpoints is used. In software, so viewpoint defines the pattern or the template for drawing the architecture of these systems. And then each drawing is called a view, architectural view. And the view actually is from one perspective of one or more stakeholders, and for a specific set of concerns. I'll skip this. Then is of course like this is the modeling part, and there are also different kinds of methods. So we have like the approach for designing methods like single system scope, multi-system scope. So multi-system is single system is of course like a single system, but you could also like I want to develop a set of systems, and we are talking more about product line or reference architecture. And then there's also how do you design the software architecture, the method. Requires a pattern domain driven. So then the questions here is like, given all these, well, okay, I have these architectural modeling, architectural methods. I did not discuss about architectural patterns or tactics or perspectives, architecture evaluations. So then the idea what I put here is like I said, as I said, I will not propose a solution, but just more like the providing context. What are the domains that are needed for a critical system of systems, right? So that's an essential question. What are the stakeholders for each of these domains, right? And so it's like each system of systems is of course different. What are the concerns? What are the architectural viewpoints? I know that the current architectural viewpoints are not sufficient to model the current critical system of systems. So we need different kind of approach. What are kind of modeling? And so we said like systems modeling, systems in a system of systems, are these sufficient? No. The architecture design methods, what are the patterns that are needed for designing this critical system of systems? Architecture evaluation method, trade-off analysis. We said like there are different kind of quality factors, and you cannot optimize for each quality. So you should actually somehow do some trade-off analysis. Governance, right? It's not just like the design, but also the whole, what are the principles, the guidelines, the management, how do you cope with that? And we have one fixed governance approach. How does it align with the existing systems? Right? So in my group, we are doing, for example, a study on governing a digital business ecosystem. So, okay, governance, there are different kinds of governance now, different kinds of platforms, but they should both be aligned. How to evaluate, how to simulate, to make sense of it, and etc. Right? So it's quite a new domain. And the problem here is like, so there's one of the last slide. We try to tackle this often using a monodisciplinary approach, right? Each from our own field, software engineering, electrical, mechanical engineering, whatever. But that's not sufficient, right? We really need to tackle it at interdisciplinary or transdisciplinary level, right? So multidisciplinary would be like, yeah, I have system of systems, and each of the disciplines could try to tackle it, but the system of systems is one holistic system by itself. It's integrated, right? It's interactive, emergent behavior with some purpose. As such, these disciplines, they should be aligned to each other, and even further, we might need to create new design abstracts, new tools. That brings me to the last slide. So critical infrastructures or critical system of systems. They are a system of systems. They are increasingly software controlled. There are many unsolved challenges, and there are plenty of research here. Right, architecting is one of the key artifacts. It's not the only artifact, but one of the key crucial issues in a critical system of systems. My perspective is like this: the systems engineering or system of systems paradigms, they need to be enhanced to cope with all these challenges. We are not there yet, and if we don't provide the right solution, we cannot properly understand. Thus, they actually are more critical than expected. For this, we need an interdisciplinary and transdisciplinary approach. This starts with starting with the systems thinking approach and system of systems thinking approach, and that requires an interdisciplinary and transdisciplinary approach. Thank you for your listening, for your attendance. I can have some questions. I hope it was.
Thank you very much, Bedir Hocam.
Mm.
Thank you all for listening. I give the word to Professor Dr. Mehmet Akşit for questions and statements.
Okay, thank you very much. Was a great talk. Why it's a great talk? Because our work also on smart cities and especially application to earthquake management is, of course, a one big, large systems of systems question.
Yes.
And I would like to say that when I started this profession, we were busy with programming in the small, and then somebody said programming in this large. And then now actually we are not only programming, creating, but more maybe truly trying to manage systems of systems. So if universities, companies, if we don't deal with such problems, we are really outdated. So we always say we cannot debug reality. Reality is systems of systems. You cannot deal with these problems with several hundred Java programs and a couple of SQL statements. No, you have to be educated to deal, I think, with systems of system concepts. And this is what we try to do at our lab with our, let's say, with a modest setup. But from that perspective, I think you gave an excellent introduction, at least, or a direction. Hopefully, people who follow this talk will be inspired. Now, of course, I want to ask people to, if they have questions, please do so. So you can also type on chat, but also directly ask. I think it's a small group, so we should be able to ask questions.
There are many master PhD topics in this domain.
Exactly. This is so exciting, actually.
Yeah, a lot.
Okay, so there should be some questions. If there are no questions, I would like to at least make statements or just to start up. When we look at actually, for example, earthquake management, of course, people try to manage now earthquakes or disaster as well, but largely manage manually or systems, yes, automized systems partially, but they are not interconnected and they don't really work in a systems fashion in an automated way. Of course, many things are carried out manually. So when, for example, earthquake happens, people report in all kinds of ways, but we don't have really that much sophisticated sensing and detecting where the disasters happen and so forth. So what we try to do, we try to, of course, try to create systems of systems in a more automated way. That means we are putting there all kinds of computer power, but also, of course, possibly cyber physical systems and all other systems, like you are also working on life sciences.
Yes.
What we realize is that actually, when we look at the criticality of the problem, the manual management actually gives up very soon. So we try to understand actually becomes a chaotic situation. So in other words, systems of systems exist also in the traditional world, but mostly done manually, and therefore
Yes.
emerging behavior is mostly unmanaged and chaotic after some point. So if you have earthquake beyond certain limit, let's say in Istanbul, everybody or anywhere, everybody is expecting a big chaos. So emergent behavior, of course, in our daily life, you showed also birds are flying and also showed some disasters in the United States.
Yes.
So that means actually systems of systems in an unmanaged manner, and also, of course, emerging behavior happens and then creates undesired emergent behavior. So the question is, of course,
Yes.
by putting automation, how
Yes.
to make it a pleasant emergent behavior, which we call it actually management. So that's, I
Yes.
think, the emergent behavior, as you stated, and to turn it into our advantage is the question, right? So
Yes, yes. So it is not, so we, for system of systems, indeed, we need to integrate systems. We had already system of systems before, like you said, and especially, we had a system, like, give, for example, the issue of a nation, right? So you put, for example, governance, right? It's that, so that you don't have chaos, right? And that's like, so that's already, because you want to have like anticipated desired result, right? It was already there, and the notion of system of systems, the systems were working together, but on a more uncontrolled manner, and sometimes the results were indeed not desired, and very often not anticipated, right? So now, if you design, if you are in engineering, you really want to actually have some goals, like in the case of health information, or in your case, like earthquake management system. You would like to ensure that all these systems which are related to earthquake threat, right? And we have like these threats, that they actually, right? So if you go here, no, it was not here, sorry. Here. You want to actually forecast it, be able that all these systems forecast it, and if you prevent, you cannot prevent some nature, but you want to be resilient and actually solve the chaos, right? So that's true. That's the idea. So I don't know whether I forgot your question, what you said, like, but the idea of like the systems, especially with software part, and also now the data science part, you can try to make sense of it, but it's also, on the other hand, also not easy. And so we went indeed from the manual to the more engineering part, but my statement here is also, but that's still not, it's still limited, because we are working from a disciplinary perspective. We should also increase the scale of our discipline that goes to the interdisciplinary level, because the problem that we wish to solve, it was like first at this single disciplinary software, for example, software level, right? And then we went to the software in the small, software in the large. Now we went to the systems level, is it? And then system of systems. But we cannot tackle these system of systems by using from one monodisciplinary perspective. So that also requires that our paradigms or tools or methods should also be leveraged, right? Increased or enhanced to cope with these new kind of problems. So I would think like, so like your lab, this is tries to take that perspective maybe, because simply otherwise it's not just the software problem, it's not just the governance problem, it's not just the communication problem. No, it's all of them together. And you want to like that they don't want, they should not interfere, but they should be synergistic in like relation to solve the things that you want to solve.
yes, so
Yeah.
the like you said, one way of doing is, of course, modeling is the key, and then simulation is another way of course, addressing this. So in our lab, we have decided to define critical performance indicators, which you have said already, attributes, but of course, every indicator and attributes you have to somehow tailor to the needs, which is in our case, for example, critical performance indicators or key performance indicators for earthquake management. And then, of course, it involves many things like, firefighters and ambulances, but we have, of course, models to deal with them. So automatically, if you work on that level, we have to be multidisciplined, at least in order to understand and model them.
Yes.
Are there more questions? If there are more questions, then I will make a small statement, and then I would like to thank to our speaker. The statement is to our students and to people who are here in this, who will listen also hopefully in the future. The really to be useful for our society, for humankind, and for our country, for our university, whatever, we have to think in the large. So we have to really tackle the real problems. We cannot just be very, very focused and forget the rest. In order to create something useful, we have to really think in the systems level. But of course, not everybody may be, you need also specialization. But in order to create such nice or useful solutions, then we have to work together. This systems thinking is also requires that we work together and form larger groups. But really addressing real problems, I think we need to have this approach. So we cannot solve the problems by writing a tiny algorithm or very focused solution, but also academicians, students, I think, work together and think large, think in the systems level. So that was my conclusion from this talk. I would like to thank Professor Bedir Tekinerdoğan very much. Çok teşekkürler hocam, sağ olun geldiğiniz için. Buradaki arkadaşlara, öğrencilere, herkese çok iyi bir ilham kaynağı oldunuz. Thank you very much to all. Thanks a lot.
Thank you for inviting me. And if you have any questions, then I will be happy to answer the questions through email. I'm on LinkedIn also, so feel free to connect with me. Thank you.
Okay, thank you. And we will have a next talk. Maybe Rabia Bilgücü can help. The next talk, I think, was on 14th, also an excellent speaker, 14th in January, if I'm not mistaken. And Semih Çetin is an excellent, has also academical part and also very much knowledgeable in applications and practice. He is the CEO of a very successful company. We will have Semih Çetin as well. Also, Bedir knows him, of course, very well. We all together. Yes. Thank you very much once again. And I also would like to thank Rabia Bilgücü for her effort and arranging this talk. Thanks a lot. Bye-bye to everybody.
Thank you. Hope to see you in Ankara as well. See you.
Okay, so.
Thank you. Thank you.